Good morning, everyone. Thank you very much for joining us in this session. This session is going to look at which methods of slices we should use when conducting our practical slope stability design and analysis, because there are so many different methods and it can be confusing which methods to use when. And so what we are going to try and do in this presentation, our whole goal is to compare the different methods of slices from practical perspectives and provide some guidance on which methods or combinations of methods we should use so that we can model a wide range of problems effectively. And by effectively, we mean we'll be able to identify the critical failure mechanisms and their associated factors of safety so that our designs will stand up and any analysis we do will be informative. So that will be our goal for this morning. And just a bit of a roadmap, we're going to look at the essentials of slope stability analysis, which will help us to understand when these methods work well and when they do not work so well. So we'll look at things like failure mechanisms, the shape of a slip surface, factor of safety. We'll look at static equilibrium. What does static equilibrium mean? And that will help us to identify which methods are best suited for what we are trying to do. And we'll also discuss the concept of the line of thrust, because the line of thrust is one of the most important criteria for evaluating whether our methods are giving us sensible answers or not. And it's not for all the methods, but you will understand when we get there which of the methods we have to be very particular when describing or analyzing the line of thrust. So that is one of the things we're going to do. Once we've done all of that, we've covered all of that material, we'll look at what methods are best for what we do. And then we will also talk just a little bit about applying numerical methods. They are a powerful tool in our arsenal, and it may be time that we use them on a more consistent basis. So once we've gone through all the methods, it will be clearer why we should be using numerical methods as well whenever we are undertaking slope stability analysis. Now, types of failure mechanisms. We do have several types. We have rotational failure, translational, planar, compound failures, which are combinations of all these. And sometimes we have wedge failures. When we get into rock, we have toppling failures, and there are different types: block toppling, flexural toppling. What we are talking about this morning focuses on rotational, translational, and planar, and combinations of these mechanisms. That is what the methods of slices will allow us to analyze. Now, we also, when doing slope stability analysis, talk about the shape of the failure surface. Originally, the methods all dealt with circular surfaces. In 2D, these are circles. In 3D, that will be spheres. With time and with advancement, particularly with the advent of computers, we now do non-circular analysis. So for most of this discussion, we will be focusing on methods that can analyze non-circular slip surfaces as well, because these tend to prevail in practice due to the presence of multiple materials, complex geometries, seismic forces, support forces, all lead to departures from circular slip surface when looking for the critical failure surface. And therefore, we will discuss more methods that deal with non-circular. But almost all of these methods, in fact, all of these methods can also easily deal with circular slip surfaces. Now let's take a minute and talk about factor of safety and what it is. It is just a measure that helps us understand how stable or unstable a slope is. And in limited equilibrium analysis is one of two very important outputs that we get. The first important output is what we discussed on the previous slide, which is the shape of the failure surface and the location of the failure surface. Another important one is the factor of safety. So whenever we run our analysis, the computer spits out a factor of safety value. And in each factor of safety value it spits out is associated with a specific slip surface. Now, factor of safety is simply your ratio of your average shear strength to the average applied shear stress. Or it can also be defined as by the factor by which we need to reduce the average shear strength available along a slip surface until it becomes equal to the average applied shear stress. A factor of 1 represents what we call critical equilibrium or limiting equilibrium. And that simply implies that the slope is at the very verge of collapse or failure. When that factor is higher than 1, the slope is stable. When it's less than 1, the slope is unstable. Now, in practical analysis, we choose some threshold values higher than 1 to which we design our slopes, but that will be a topic for another day. We're not going to go into the details of that this morning. The different methods that we use for slope stability analysis are the limit equilibrium methods, limit analysis methods, which we will not talk about any further today, and numerical methods, which we will discuss not into detail, but we'll definitely talk about a little bit later in our talk. Limit equilibrium methods, also known as methods of slices, and we'll see an image and you'll see why we call them that way, are the most common slope stability methods. They are relatively simple and fast, and engineers have had experience with these methods for over 100 years, and they are very useful for evaluating the sensitivity of slopes to different conditions and input parameters. And therefore, they can also be readily used for probabilistic analysis. Now, another thing we use in slope stability are these limit equilibrium methods. Very fundamental to how these methods work is statics. So there are different equations of statics, if we remember from our undergrad studies. Summation of forces in 2 directions, and we typically sum forces in the vertical and horizontal directions, and then summation of moments around an axis. If all of these equations are satisfied, we say we have established complete equilibrium. So these limit equilibrium methods look at these, implement or look at that in our system of equations. When we look at all of these, we may not have enough equations given a number of variables to solve the problem. We say the problem may not be determinate. And in that case, we need to make certain assumptions to be able to resolve the situation. So let's look at the method of slices. There is a failure volume which we have divided into these vertical slices. So the picture you are seeing is for the vertical slice methods. There are a few techniques that can consider non-vertical slices. Well, most of the techniques we talk about today will consider vertical slices. Now, for each slice, there are inter-slice forces, as we call them. These forces are inclined at some angle, and we resolve them into shear components and normal components. Then there are forces acting at the base of the slices. And remember, the base of the slice is the failure surface. So there are forces acting at the base of the slices, which again we resolve in analysis. So we're going to talk about that in a little bit. But when we sum up all the number of unknowns, n being the number of vertical slices, we end up with 6n minus 2 unknowns. These are the variables we're trying to solve for. But when we put together all the static equations for each slice and we combine it with the failure criteria, we end up being short of this number of unknowns. We will be short by n minus 2, which means that we do not have enough equations to match the number of unknowns. So what do? It means we need to make certain assumptions to make the problem statically, the problem determinate. And so the different methods that we talk about, and we will focus on 6 of them today, but based on the assumptions they make, there are more than 10 methods available. But we will focus on 6 of the most popular, because these will capture practically the behavior of all the others that we don't discuss, and we can apply these same principles to analyzing any other methods that we don't look at into detail today. Not all the methods satisfy all of these equilibrium conditions, but some of them do, and the ones that do we call rigorous methods. Now, with the rigorous methods, the line of thrust becomes a very important criterion for evaluating how correct their results are. It simply means that for each slice, we look at the location of application of the inter-slice forces. When we join these locations with a line, that line is called the line of thrust. And we will see how important it is to take into account the line of thrust whenever we are talking about the rigorous methods of analysis. The different methods make different assumptions or handle the location of the line of thrust differently. The simple ones, like the Bishop and the Janbu, the ordinary, and we'll talk about them, simply neglect the line of thrust. So you don't even need to plot them. It doesn't exist in these methods. When we go into a method like the GLE, which means Generalized Limit Equilibrium method, it assumes a line of thrust. The Spencer, Morgenstern, and Sarma methods calculate the line of thrust as part of the computations in solving the equations of equilibrium. Now, the most popular methods is the ordinary, the Bishop Simplified, Janbu Simplified, Spencer, Morgenstern Price, Generalized Limit Equilibrium. We have grouped these two because under certain conditions, the Morgenstern Price is a unique case of the Generalized Limit Equilibrium. And the way it is implemented in some software, including Rocscience slide 2, slide 3, make these two methods equivalent. And then there's the Sarma method. So these we are going to look at. So what we'll do is we'll look at very quickly what assumptions they use, what equations of equilibrium they satisfy or do not satisfy, and how do they converge. Convergence is an important part of it. When you are solving for any given failure surface, you try to solve these equations for a factor of safety. It is not every surface that will give us a factor of safety. Sometimes some of these methods can run into convergence problems. So we'll discuss that for each of these methods. So the ordinary method is one of the simplest methods, and as you can guess, it's one of the oldest methods. It neglects interslice shear forces, and as a result, equilibrium is not satisfied between slices. But the beauty of this method is it does not have convergence problems because it does not iterate. It's a very simple equation to solve for factor of safety. Now, it tends to give conservative answers, which means it tends to underestimate the factor of safety. As a result, designs done on using the ordinary slice method are likely to be on the safer side. The only problem is sometimes the underestimation as high as 60%, and that would mean your slope design would be uneconomical. So that is why the ordinary, although it is on the safer side, may not be the best to use for practical analysis. It may be appropriate for non-homogeneous slopes, so multiple materials and C5 materials when you are using a circular surface. As we said, the factor of safety can be very inaccurate, particularly when slopes are flat and have high pore pressures. So we have to be aware of this deficiency of the ordinary method. The Bishop Simplified method neglects interslice shear forces, but it does it in such a way that it satisfies vertical force equilibrium and moment equilibrium, but it does not satisfy horizontal force equilibrium. And then it can start running into convergence problems. And as we said, because it does not satisfy horizontal force equilibrium, sometimes when you are using it for non-circular analysis, experts tell us that moment equilibrium can become iffy. So some, in fact, say we should not use them for non-circular analysis, but people have also used them for non-circular analysis very successfully. So it's still available to us. We must understand that as simple as this method is, it is known to produce factor of safety values that typically are within just a few percentage points of what we'll call correct values. Those are the values from rigorous methods when they converge to the true critical surface. So the Bishop is simple, but it's very useful because it often gives values similar to those of rigorous methods. Then there's a Janbu method. It satisfies force equilibrium, vertical, horizontal force equilibrium, but not moments. And it tries to use a correction factor to account for interslice shear forces. It can also experience convergence problems similar to the Bishop, same conditions, but its computations are very fast. And again, because it satisfies force equilibrium, that gives it advantages when you're looking at, for example, seismic analysis or pseudostatic seismic analysis. because we are looking at horizontal forces, Janbu can be very helpful in those situations. Then the Morgenstern-Price NGLE method. Morgenstern-Price was probably the first method developed that satisfied all the static conditions of equilibrium. To do so, it makes certain assumptions about the interslice forces, and it uses an arbitrary mathematical function to represent the direction of these forces. It gained a good reputation very quickly, until today remains one of the most popular methods. It's one of the gold standards, if we may call that, in limited equilibrium analysis. The GLE method is a more generalized version, but under certain assumptions, you get the Morgenstern-Price method out of it. That's why we equate them in our current discussion. When you have very high cohesion, then what happens is your interslice forces, when it tries to solve the equilibrium, it can generate tension. And we'll see whether this is acceptable or not. But sometimes to eliminate the tension, you will need to apply tension cracks in your model. Then there is a Spencer method. Of the rigorous methods, is the most simple. So it satisfies all static equilibrium conditions. Unlike, Morgenstern-Price used some mathematical relationship to represent the direction of the interslice forces. In the Spencer, it assumes a constant interslice force for all the slices. It also runs into convergence problems as it searches for the lowest factor of safety surface, but it can be applied to virtually all slopes. It is very suitable for problems which have horizontal forces like seismic or pseudostatic seismic analysis, or when you have support in a slope. But again, you might have to use a tension crack to deal with some of the problems. Otherwise, you will not get acceptable positions of the line of thrust. Very important. And when you look at your line of thrust and you are struggling with it, you don't like it, it seems to be problematic, you may have to include tension cracks in order to resolve the problem. But we will look at that a little in our discussion. We'll talk about that again. Now, the Sarma method, it uses interslice assumptions similar to Morgenstern-Price, except the slices do not have to be vertical. So of all the methods we are discussing this morning, it is the one that can handle not vertical slices. It comes up in its solution technique, it looks for a certain horizontal acceleration that brings the slope mass to failure, or to the very verge of failure. And as part of doing that, it can calculate a factor of safety. And this factor of safety, the factor of safety will give you a critical acceleration which is equal to 0. So these are just some of the underpinnings of the method. We don't need to know all the details of the mathematics of it, but this just gives us a general idea of how Sarma works. And it's generally suited to complex problems because it can accommodate non-vertical slices. Another interesting thing about Sarma is if you have joints, discontinuities in a slope model, it is quite easy to use the Sarma because you can represent the different strength of these discontinuities. You can put slices along those discontinuities and use different strength to represent them. The other methods do not allow you to do that. So that is one of the advantages of the Sarma method. Now, it is important that for the solution to be acceptable, you must make sure that all the normal forces acting on the base and on the sides are positive. Very key to understanding whether the Sarma is giving you acceptable results or not. So just a summary of these static equations. One, ordinary method does not satisfy horizontal or vertical equilibrium, but moment. Bishop, not horizontal, but vertical and moment. And down we go the list. The three that satisfy full equilibrium are Spencer, GLE, Morgenstern-Price, and Sarma. Now, a few notes on these methods. So the Spencer, Morgenstern-Price factors of safety tend to be generally similar. And not only are they similar amongst themselves, but they are also similar to the simplified Bishop factors of safety. Spencer, Morgenstern, Price, GLE, and Sarma, in trying to realistically estimate interslice forces, that's why they come up with fancy assumptions for them, tend to give you higher factors of safety than you will find with the simpler methods like Bishop and Janbu Simplified. So important to keep that in mind. Now, we need to check the validity of our factor of safety results. So Whitman and Bailey wrote, and this is all the way back in 1967, that the use of the Morgenstern Price method together with a computer does not free the engineer from making judgments concerning the reasonableness of solutions. This remains so true today, and that is what we are going to spend some time discussing now. As a user, you must always check your solutions to make sure they are physically valid. And what do we mean by physically valid or reasonable answers? It means that we have to check, we'll get to it, the line of thrust, but it's extremely important. The methods for checking exist, but very often in practice, we do not check. And I hope that after today, all of us will make it a practice to check the results of our limit equilibrium analysis. And these authors named here, Morgenstern, Price, Whitman, and Bailey, in different papers, argue that we should accept, for the rigorous methods, we should only accept solutions that, one, do not violate failure criteria of soil or the masses, the failure masses, and do not cause tension in the materials. They strictly insist on that. So ideally, our line of trust should exist within the failure mass. It should not go outside the boundary of the sliding mass. And if it goes outside, which typically happens when there is tension, or in pseudostatic analysis when you have high horizontal forces, they can also throw it off. We may have to consider whether the line of thrust is acceptable or not, because it will go outside the sliding mass. And the rigorous methods experience challenges in tension cracks in order to deal with the tension that occurs. So these line of thrust problems also occur when we have high effective stresses, when you have high pore pressures. So let us remember that that does happen sometimes, and we can eliminate them with tensile cracks, tension cracks. But sometimes in doing so, it makes the problem unrealistic. Let me add that tension cracks are not a panacea to every problem of the rigorous methods. So you may have to judge whether it is good enough, or whether adding tension cracks really improves the solution. Now, when you have funny shaped failure surfaces, because when you have multiple materials, sometimes you can have kinks or humps in the failure surface. Then, especially these rigorous methods can start giving you funny answers. They will develop negative interslice forces, and you would have to check whether these forces or whether these solutions are good enough, because in such cases, your factor of safety might actually not be conservative at all. And that is why it's important to pay attention to this line of thrust discussion. If you don't pay attention, you can end up with a solution that is not conservative. That can be dangerous. When you have such funny surfaces, make sure you critically analyze the things we are talking about: line of thrust, presence of tension. If you find them unacceptable, you may have to, and these methods allow you to change your interslice assumptions. So sometimes you may have to go back and change your interslice assumptions to see whether you get a better answer. But as engineers, we must always, so that's one of the things we'll say, always check your line of thrust when you use the rigorous methods. It's something we must practice almost as a religion. Now, what are the best methods? You've seen that we've spoken about 6 of the most popular methods. We've looked at when they are best used and when they are not so good. And the question is, so how do we combine all of these and use them? There's no universal method, we've learned, and it's necessary, it may be necessary to use more than one. So even as for experienced engineers, we need to know which of these methods we should use when. And so what we are going to try and come up with is methods that just allow us to capture the true situation without change its location and its factor of safety. So that's what we're going to try and do. So first thing that we will learn from literature when we extensively review is that, as Morgenstern and as suggested by many authors, the Morgenstern, Price, and Spencer methods are very highly preferred. In many publications, you will come across that. Two, Bishop and Janbu, may be much simpler methods, but their results actually typically compare well, and they tend to be on the lower side. They tend to give a more conservative factor of safety. So that is another reason why these methods, although very simple, are quite popular. We should not assume that because we are using full or rigorous methods, those methods are necessarily more accurate, because they may not converge, or sometimes they can converge to strange or physically unacceptable results. So we must always, and again, as we said earlier, always practice checking the results of our rigorous methods, line of thrust, presence of tension, to make sure that they are acceptable. So what do we do? Since Spencer, Morgenstern, Price are widely respected and recommended, we say use them. But in addition to using them, use also the Bishop and the Janbu. The Bishop, I say, use as a police check. And the next slide is going to be a little funny, but it is so true with what we do. Of course, I trust your judgment, dear daughter, but it can't hurt to do a quick police check on your new boyfriend. So what happens is, even though you have your rigorous methods and they give you results, you want to be able to check them. And the Bishop is a good check. So Bishop will allow you to see whether the rigorous solutions have converged to the critical mechanism or not. So sometimes what you notice is Bishop may give you a far lower factor of safety for a certain slip surface that may not appear in the Spencer and Morgenstern Price analysis. So that will be an indication to you that those two, where the two rigorous methods were struggling with convergence, and therefore you probably have to rely more on the Bishop answer in that case. So very important to use Bishop and Janbu as check. So ultimately, we are saying use Bishop, Janbu, Spencer, Morgenstern, Price, compute for them, check how the Bishop and Janbu compare to the rigorous methods results, and make sure that the rigorous methods have converged. If they've converged, use the rigorous method results. If they have not converged, and therefore are much higher than what you notice for the Bishop and Janbu, then you may have to use the Bishop and Janbu results. So this is how we would go about using this toolkit. Now, talking about numerical methods, they have certain advantages and of course disadvantages compared to the limited equilibrium methods we've looked at. We look at so many exceptions with limited equilibrium methods and things to look out for and lines of trust, all these things that we have to pay attention to. When situations are complex and you have coupled behavior, you have sophisticated material strength behavior, you may be better off using numerical methods. And numerical methods, even for the simple situations, will give you another result that can help you ascertain whether your limited equilibrium results are acceptable or not. One, numerical methods do not need trial and error to determine the critical failure surface. It just naturally comes out of the analysis. The failure surface will go through materials that cannot sustain the applied shear stress. It just comes out. They satisfy all the equations of equilibrium. They also satisfy additional equations, which are called compatibility equations. So they are more robust from that perspective. If you put in reliable information on the Young's modulus, Poisson's ratio of the materials, you can actually get displacements of the slope, which is something we monitor. So these methods can be very helpful even in us coming up with monitoring of slopes. Limited equilibriums do not give us any information on displacements or deformations. So it is important that we also try the numerical methods because they give us another picture that can help us determine whether we have found a critical failure mechanisms and factors of safety of slopes or not. They have some additional advantages. We can look at them in the slides that we will provide later on. So just to sum up everything we have said for this one, start with limit equilibrium methods, Bishop, Janbu, Spencer, Morgenstern, Price, GLE. And check for Spencer and Morgenstern, Price, always make sure you check the line of thrust and also check the presence of tension. Now, people have also told us, after all of this, some researchers tell us that even the physically unacceptable methods sometimes have factors of safety that are not too far from the acceptable methods. That's another challenge that can occur with the limit equilibrium methods. So use shear stress reduction analysis with any of the numerical methods as another backup. With this picture, you will be able to say you have looked at the factors of safety of your slope, and you can be more confident that you have found the right things you need to find to come up with safe economic designs. Thank you very much. And here are some references at the end that you can use to further study what we have spoken about.